Hi, welcome to Introduction to Bayes' Theorem. In this video, we're going to give a very basic introduction to Bayes' theorem. Bayes' theorem is an important result in probability. It is additionally important for evaluating the probability for a hypothesis to be true. Let's say you have a hypothesis which you want to test. You design an experiment and you do an analysis to figure out if the hypothesis is true, the probabilities of different outcomes of the experiment. But after you perform the experiment, what you actually want is the opposite. Given the outcome of the experiment, what is the probability that your hypothesis is true? Bayes' theorem helps us relate these two probabilities. We'll cover the importance and some applications of Bayes' theorem in other videos. Here, we'll present Bayes' theorem and go through a simple example to get a feel for what the theorem means. Okay, let's get started. Okay, so first, let's define some notation. So first of all, P of A is the probability of A. So for example, P of rain in Paris tomorrow is the probability of rain in Paris tomorrow. Also, P of A given B is the probability of A given that B is true. So, P of rain in Paris tomorrow given cloudy in Paris today is the probability of rain in Paris tomorrow given that it is cloudy in Paris today. P of A given B is called a conditional probability. So Bayes' theorem is the following. The probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Let's see how this works out in a simple example. Let's say we have a collection of 10 objects. 7 of them are squares and 3 of them are circles. Additionally, 4 of the squares are purple and 3 are green. Similarly, 1 of the circles is purple and 2 are green. We'll choose one of the objects at random. All of the objects are equally likely to be chosen. What is the probability that the object we choose is a square, so P of square? Similarly, what are P of circle, P of purple, and P of green? Let's quickly write these down. First, P of square. To do this, we'll imagine that we choose an object and then take note of whether or not it is square. We then put the object back in the bunch and repeat the whole process many times. P of square is the fraction of the time that the object we choose is a square. Of the 10 objects, 7 are square. So 7/10 of the time we choose a square object. This means that P of square is equal to 7/10. Also, out of the 10 objects, 3 are circles, so P of circle equals 3/10. Okay, next P of purple and P of green. Out of the 10 objects, 5 are purple and 5 are green. So P of purple equals 5/10 and P of green also equals 5/10. Okay, so we have P of square equals 7/10, P of circle equals 3/10, P of purple equals 5/10, and P of green also equals 5/10. Now let's try something a bit less straightforward. So what is P of purple given square, the probability that the object is purple given that the object is a square. To answer this, imagine we choose an object, note whether or not it is a square, and if it is a square, note whether or not it is purple. We then put the object back in the bunch and repeat this exercise many times. There are 7 square objects. Of these, 4 are purple. So, out of all the times we choose a square, in 4/7 of those instances, the object will also be purple. So P of purple, given square, equals 4/7. Okay, now what's P of square given purple? The probability that the object is a square given that it is purple. So out of the 5 purple objects, 4 are square. This means that P of square given purple is equal to 4/5. We could similarly work out the conditional probabilities involving circles and green objects. So here are our results so far, in the table at right. Let's plug these values into Bayes' theorem and make sure it works out. Okay, so again, here we have Bayes' theorem. The probability of A given B equals the probability of B given A times the probability of A over the probability of B. Let's write this for A equals square and B equals purple. So that gives us the probability of square given purple is equal to the probability of purple given square times the probability of square divided by the probability of purple. Let's substitute in the values we've obtained and see if it works. Okay, so again, we have Bayes' theorem. We're going to substitute in the values from the table. So P of square given purple was equal to 4/5. P of purple given square was equal to 4/7. P of square was equal to 7/10, and P of purple was equal to 5/10. So we have to check, is 4/5 equal to 4/7 times 7/10 divided by 5/10? And in fact it is. So it works. So it's good to know that Bayes' theorem works in this example. Now let's see if we can understand why a bit better. Let's look again at how we got each of the factors in our equation. So let's look at P of square given purple, P of purple given square, P of square, and P of purple. So we obtained P of square by dividing the number of square objects, 7, by the total number of objects, 10. We similarly got P of purple by dividing the number of purple objects, 5, by the total number of objects. We got P of square given purple by dividing the number of square purple objects, 4, by the number of purple objects, 5. And finally, we got P of purple given square by taking the number of purple square objects, 4, and dividing that by the number of square objects, 7. So let's put this all back into our equation. So, on the left-hand side, we had P of square given purple. That becomes the number of square purple objects over the number of purple objects. On the right-hand side, we have 3 factors that we need to worry about. The first one is P of purple given square. That's equal to the number of purple square objects divided by the number of square objects. The next one is P of square. That's the number of square objects over the number of objects. and the one in the denominator, P of purple, is equal to the number of purple objects over the number of objects. We can see that this holds because on the right-hand side, the factors of number of square objects, here shown in blue, cancel out, and the factors of the number of objects, here shown in red, also cancel out. And so on the left-hand side, we have the number of square purple objects over the number of purple objects. And on the right-hand side, we're left with the number of purple square objects over the number of purple objects. So note that the number of square purple objects is the same as the number of purple square objects. Perhaps we'll get a bit more insight, however, by moving the denominator on the right-hand side over to the left-hand side. So we get on the left-hand side the number of square purple objects over the number of purple objects times the number of purple objects over the number of objects. And on the right-hand side, we get the number of purple square objects over the number of square objects times the number of square objects over the number of objects. Let's also multiply both sides by the number of objects and look at both sides of the equation. Okay, so on the left-hand side, we have the two factors, the number of purple objects over the number of objects times the number of objects. This just gives the number of purple objects. We then multiply this by the number of square purple objects over the number of purple objects to get the number of purple objects which are also square. On the right-hand side of our equation, we have the number of square objects over the number of objects times the number of objects, which just gives the number of square objects. We then multiply that by the number of purple square objects over the number of square objects to get the number of square objects which are also purple. So if we start with all of the objects and either 1. Take the objects which are purple and from them select the objects which are square, or 2. Take the objects which are square and from them select the objects which are purple, we end up selecting the objects which are both purple and square. In our example, Bayes' theorem is just an expression of this fact. Okay, let's see if we can now understand Bayes' theorem more generally. So it was the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Like we did with the example, let's move the denominator on the right-hand side over to the left. So this gives us the probability of A given B times the probability of B equals the probability of B given A times the probability of A. Okay, so we have that equation from the previous slide. Let's look at the left-hand side. P of B is the probability that B is true. P of A given B is the probability that A is true given that B is true. Now, P of A given B times P of B is just the probability that both A and B are true. So P of A given B times P of B equals the probability of A and B. Now let's look at the right-hand side of the same equation. P of A is the probability that A is true. P of B given A is the probability that B is true given that A is true. P of B given A times P of A is the probability that both B and A are true. So P of B given A times P of A just equals the probability of B and A. So Bayes' theorem, slightly rewritten by moving P of B from the denominator in the right-hand side over to the left-hand side, is simply a statement that P of A and B equals P of B and A. So that turns out to be not so complicated after all. Let's quickly link this back to the case of our example. There, this took the form of P of square and purple equals P of purple and square. Okay, so let's summarize. Bayes' theorem is an important result in probability and is useful for evaluating the probability for a hypothesis to be true given some observation. Here, we've given a quick introduction to Bayes' theorem using an example of randomly choosing objects of different colors and shapes out of a set. Through this, we saw that Bayes' theorem is a statement that the probability that both A and B are true is equal to the probability that both B and A are true.